All right, ladies and gentlemen, today we want to take a look at energy with our simple harmonic oscillator, and we're going to do it very much in the same way that we dealt with energy with gravity, with kinetic and potential. And if you remember this equation, we had mgh plus 1/2 mv squared. That was our potential energy due to gravity, and this was kinetic energy. And we said that as long as there's no non-conservative forces, there's no friction, there's nobody pushing or pulling on anything, then whatever this sum is to start with, sort of at the initial point, then at the final point, those two individual things can change, but overall, that sum has to be equal. Our total energy, our total mechanical energy at the beginning, has to equal our total mechanical energy at the end. And that's going to remain true with these springs as well. We are not going to have any outside forces. It turns out that the spring force that we talked about with Hooke's law is a conservative force. So because of that, we get to conserve all of our energy whenever a spring or any harmonic oscillator acts. But instead of having this gravitational potential energy, we're actually going to substitute that out for what is called spring or elastic potential energy. So the equations that we will use are 1/2 kx squared instead of mgh, but we still have that same 1/2 mv squared. So our potential energy that is stored in a spring, 1/2 kx squared, plus our kinetic energy equals our total mechanical energy. And we get to treat these just the same way as we did in our previous just gravity unit with energy, gravitational potential energy, when we first were introduced to energy and power and work. A couple sort of positions that we will be in with this. First, I want to draw a little graph, position versus time. We've seen this one before. I'm actually going to make a nice equilibrium position here. And let's say we had some oscillating body across one period, just like we've seen before. We will call this A for the amplitude and negative A, and 0 here at the equilibrium position. At the equilibrium position, we said in the last video that our velocity is at its maximum. If our velocity is at its maximum, then that means our kinetic energy is also at its max. In fact, the kinetic energy equals the total mechanical energy, and our potential energy from that spring is 0. That's because if we plug in for that 1/2 kx squared for our potential energy, x is 0 at the equilibrium position. So that whole setup just becomes 0. The same is true up here at the top. Up here at the top, our potential energy is at its max, and the same thing is true down here at the trough as well. At these two positions, our x is at its maximum, and our velocity is 0. Our velocity is 0 at both these points. We come to a quick stop. If the velocity is 0, then when we do 1/2 mv squared for our kinetic energy is also equal to 0. So at our equilibrium position, we have all kinetic energy and no potential energy. At our peaks and troughs, so here and here, we have just potential energy, no kinetic energy. And anywhere in between, we have some combination of both. But whatever that combination is, it still has to add up to either the potential energy max or the kinetic energy max, both of which are total mechanical energy. Whatever our combination of energy is, it has to equal up to the exact same thing at any point along this oscillation. So just to kind of summarize that, at our equilibrium point, our velocity is at its max, which means that the kinetic energy is equal to our total mechanical energy because our potential energy due to the spring is 0. At the amplitude or the negative amplitude, either one works, our velocity is 0, which means that our kinetic energy is 0, which means that our potential energy from the spring is equal to our total mechanical energy. Anywhere else, we have to have a combination of kinetic plus potential energy to get our total mechanical energy. Those are really our 3 options as we go through some of these problems. So I want to go through and just kind of solve one of these. Let's say, for instance, that we had a spring that was hanging vertically, and it had a mass on it. The spring constant, I'm going to say, is 100 newtons per meter. And it's a 3 kilogram mass. And we are going to extend it down. So now it has been extended down. And the distance that we extended it down, we'll say it was 0.5 meters. Our first question is going to be, what is the total mechanical energy? Is really what we're looking for. That lets us solve any other problem. So back from that last slide, we have 3 options. Either right now, at this extended point, we have just kinetic, just potential, or some combination of both. Well, right off the bat, the kinetic is not going to be at the max, right? We extended it from the equilibrium. That means it's not at equilibrium. So our total mechanical energy has to at least have some potential energy with it. In fact, it's only going to be potential energy. If we extend a spring downward and then we're getting ready to let it go, that means we have extended it, the amplitude. This 0.5 meters that we extended it is the amplitude. We're holding it at rest at the bottom there of that spring. So our total mechanical energy is made up just of potential energy at this point. So really our total mechanical energy is going to be 1/2 times that spring constant from before, that 100, times the distance that we extended it squared, so 0.5 squared. This becomes 0.25, so we get 100 times that, and then times 1/2. So 1/2 of 25 is 12.5 is our total mechanical energy, and that is in joules. That is also equal to our potential energy at equilibrium. So a question could ask you for either, it could say, I'm sorry, not at equilibrium. That is at the peak or trough, at the amplitude. That's what I'll call it. At the amplitude, that is our potential energy. So a problem could ask for either one. It could say, at that point that it's been stretched to, what's its potential energy, or what is the total mechanical energy of the object at that point. Either one is fair game, but the answer is the same regardless. Next question up for this, I'm going to kind of shrink this down a little bit. The next question up is, how fast is my object going when it gets to the equilibrium? When it gets to the equilibrium, that 12.5 that we solved for before still has to be the total mechanical energy. Any point along the oscillation, whether it's somewhere in the middle, at equilibrium, at a peak or a trough, the total mechanical energy that we started with, that we gave it when we sort of loaded it up with energy as it got stretched, that 12.5 has to stay throughout. So now at 12.5 as my total mechanical energy, The question is, at equilibrium, how fast is it moving? Well, at equilibrium, we only have kinetic energy. So that 12.5 has to be only 1/2 mv squared. At that equilibrium, we've got a 0 for our potential energy. So that's just a matter of plugging some more stuff in and solving. I'm going to multiply both sides by 2 to get this to 25, equaling mass of 3 kilograms times that velocity. There's that mass again. Divide both sides by 3. It's 8 1/3 equals v squared. And then the velocity is whatever the square root of 8.33 is. Should be a little less than 3, and it appears to be 2.89 meters per second. 2.89 meters per second. That is sort of the extent that these problems will go through, and there's a lot of variations on them. Make sure you're working on worksheet 3 in the packet. Is a wonderful resource for getting ready for the test. A lot of different questions. I will say that questions like numbers 9 and 10, where there are multiple steps, are good examples to go from. All right, the last idea we want to hit for this is the idea of a potential energy versus time graph. And I'm going to lay out a position time graph with it so we can go through kind of both of those at the same time. And again, that position time graph, we need that equilibrium to be here in the middle because we go up and down from that equilibrium. So I'm just going to give it a nice little shape, maybe a period or 2 or 3. And those are relatively the same height. Those amplitudes should be the same height. They're not quite, but we'll call this the amplitude A, we'll call this negative A, and we'll call this 0. We'll give it some time, 1, 2, all the way down. I'm making it easy on myself, keeping it nice and simple. And right now we have a 4-second period. So our period here is 4 seconds, our amplitude is A. And the question becomes, all right, we're going to draw out where our potential energy is at each of these times, each point really that we have at each second. And I'm going to try to line these up as best as I can so that we have an even-ish, maybe right there, here, graph. These two graphs are going to be of the same object. We're just looking at slightly different things on each graph. So for this first one, at certain points, being the peaks and the troughs, we have a maximum potential energy. So I'll just say, for the sake of argument, we'll just call it 10 as our maximum. So at any peak or trough, I get a maximum potential energy. That's because I have loaded whether I compress or expand the spring. It doesn't really matter. At either of those situations, whether it's fully compressed or fully expanded, I have as much potential energy as I can get. That spring is ready to start moving at that point, back to that equilibrium. And at that equilibrium, I have absolutely no potential energy. So for each of these points where it hits the equilibrium, my potential energy is 0. And what you'll notice is as I draw this, it looks very similar to the graph up above it, but it might just be a little bit more scrunched up. And that proves problematic for some people, especially if you're asked to get the period off this graph. It is still going to be 4 seconds, right? This is the same exact object, but one period now looks a little bit different. Before we said it just went from peak to peak like it does here. But now this goes from peak to second peak, or trough to second trough. And that's because of what this graph actually represents. So we said here that our object started from the top of its motion. We can see that up here with that amplitude. And then as it falls down to this equilibrium position, we said that's where the 0 is, it continues down. So even though this is a peak, this is actually, all right, bottom instead of down, But this peak on the energy graph is actually when the object is at the bottom of its motion. See, it lines up with that trough from up above. So we go back to the equilibrium and then up to the top. So really we went peak to peak in distance, but we went a couple of peaks on our energy graph. That is one of the things. And writing out on each one of those peaks where your object is a wonderful habit to get into. It will always alternate top, bottom, top, bottom, top, bottom, or starting with bottom and going from there. Just double check the question and see how that gets laid out. If it says it is released from the top, this first one is going to be a top. If it says it's released from the bottom, that one's going to be a bottom. And we can also get a little bit more information that will allow us to do problems like we did before when we're just given this graph to start with. And the biggest thing is at this peak, that whatever that number is, whatever I read over from the y-axis, that is my total mechanical energy, right? At those peaks and troughs, I'm only made up of potential energy. My object only has potential energy. So whatever value we have here, 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 and here, that's the total mechanical energy. It's my potential energy maximum. And because of that, we can get our total mechanical energy, and then we can continue from there to do the types of problems we had on the last sort of worksheet, that worksheet 3. So let's just take a look at one example of some of the stuff we can find here, and that is you can actually get your spring constant from this graph as long as you're given the amplitude. So let's say my amplitude is 0.4, and I want to know what my spring constant is. So I don't know what it is. The equation that relates potential energy to spring constant, my potential energy is 1/2 kx squared. I don't really know, I don't know all of my x positions. I can't just pick any x, but it did give me 0.4 as my amplitude, and that is a displacement. I can use that in this equation. If I'm going to use that, though, I have to have a potential energy that matches up with when I'm at the amplitude. So go back to the graph. Oh, look, I've got a nicely marked piece that says I'm at the top. That would be my amplitude. And I get a potential energy just by reading that graph, picking the piece off of that, getting my y value of 10. So then I have 10 equals 1/2 k times 0.4 squared. So I get 20 equals 0.16 k. Divide that, let's see, 20, oh, there we go, 20 over 0.16, and I get 125 newtons per meter. So you can get our spring constant from this. We can also get our velocity at the equilibrium. If we know the total mechanical energy, if we just look at those peaks, that is the same amount of energy, of kinetic energy that we have at the equilibrium. So we can get a lot of different information from these graphs. It's just a matter of really finding your total mechanical energy. That's the biggest thing. Start there, and everything else should relatively come together in either having the potential energy at a maximum, having the kinetic energy at a maximum, or having some combination of the two.